Geothermal Overview, Opportunities, and Challenges. The goal of this session is to build a strong foundation for understanding geothermal energy by exploring resource types, technology stacks, today's market landscape, and the key opportunities and challenges shaping the future of geothermal development. We're also exploring how data analytics and AI can help define the opportunity and address key challenges in the field. Before we begin this session, I would like to invite Ms. Sushma Bhan, SPE Technical Director for Data Science and Engineering Analytics, also known as DSEA in short. DSEA is currently SPE's largest community with 4 technical sections. Ms. Bhan has been instrumental in bringing together this initiative and connecting technical leadership, industry experience, and data-driven perspectives within SPE. I would also like to invite Dr. Pushpesh Sharma, Chair of SPE DSEA Technical Section and Product Manager at Emerson, to share a few remarks. Thank you for joining us today. I will now turn it over to Ms. Bhan and Dr. Sharma for opening remarks.
Sushma, are you there?
Yes.
Okay, awesome.
Welcome, everyone. And this is indeed a pleasure and privilege to have kicking off our SPE Data Science and Engineering Analytics Geothermal Learn-to-Launch Initiative. Just to give you a big picture view, SPEI, which is SPE International, and Project Inner Space, they formed a collaboration which wants to basically expand, grow, bring innovation, and expand the whole geothermal focus. And this is being done through all the technical disciplines. And since I'm the technical director of data science and engineering analytics, it's truly my honor to have this opportunity. And what we are looking at is how can we look at end-to-end value chain of geothermal? How can we make it more unified with the subsurface data? How do we bring more AI innovation? I know Pushpesh is a big fan of agentic AI. Can we do autonomous decisions? Leveraging drones, for surveillance, for bringing more safety, robotics. So kind of sky's the limit when we look through the DSEA lenses. It's a huge discipline, and we want to make sure that we are looking at every aspect from reservoirs to drilling to completions to production and safety. And how can we do it in more integrated manner, faster, more economical? It can be more safer, scalable, and sustainable. So that is our main agenda. How this initiative will forge forward, I'm going to ask Pushpesh Sharma, who has been, again, the chair of Data Science Engineering Technical Section. He has experience based on our initial geothermal datathons and other initiatives. So he's going to share a little bit of how we are going to take this forward through this initiative. And we are really honored and privileged to have our first key speaker who you'll hear more about. So we are really counting on industry's best minds. We're counting on practitioners, we're counting on leaders and experts who will come also from academia to enrich and educate and give the basics and fundamentals of geothermal. And then we want to make sure that our members are going to take this forward with innovation right from start to launch of an initiative. So with that, I want to say again, welcome, and we are very excited. I'll hand it over to Pushpesh Sharma.
Yeah, thank you, Sushma. So I'll quickly walk over some of the logistics for the overall initiative, and I know everybody's waiting for Dr. Horne to start talking, so I won't take too much time. But this is, as Sushma mentioned, the initiative that we are trying to pursue in 3 phases. First phase is the core learning webinar series, so that's where we are today. So we want to start with a lot of knowledge covering the ground to understand geothermal, and a lot of you already know about geothermal. So this is just to level set everybody, and the focus is actually to understand what are the challenges in geothermal and how DSEA new technologies can bridge the gap and eventually make geothermal a more sustainable business. So We are today here. We are starting with geothermal overview opportunities and challenges with Dr. Roland Horne. And after that next one, we are planning a resource to return. This is more finance and economics driven panel discussion. So this will be another way to kind of for all of you to understand the current challenges, especially focusing on economics and finances of geothermal. And there will be other subsequent sessions around drilling, subsurface, surface, AI, agentic AI, and robotics, and eventually geothermal digital twin. So our hope is to then bring it all together into a business plan competition, GeoVenture Launchpad, and the goal is to promote all that and everybody to kind of think about different ideas. And our hope is that based on all these different sessions, you will start gathering some of the challenges that we can tackle with this new technologies and innovation. So, and then how do you build it up into a business? So that's going to be the business plan competition. We'll share more detail over social media and our SPE channels. And then overall, after the competition, we'll pick top 3 teams. They will be invited for a innovation spotlight. It's more like a Shark Tank type presentation. So that's our plan. So I'll just quickly thank the team here. We have a lot of good volunteers, mostly students: Havila, Chinaza, Divya, Sinar, Mercy, Mingliang, me, and Sushma. So just wanted to let everybody know that please follow our LinkedIn page. And we also have a YouTube channel where we plan to post all the videos from these events. So all the knowledge is stored for future references. With that, Divya, without wasting any more time, I'll hand it back to you. Thank you.
Thank you, Dr. Sharma. It is now my honor to introduce today's distinguished speaker, Dr. Ronald Horne. Dr. Horne is a member of the National Academy of Engineering and director of the Stanford Geothermal Program, which is now in its 55th year. He also served as president of the International Geothermal Association from 2010 to 2013 and as the chairman of the World Geothermal Congress in 2005, 2010, 2015, 2020, and 2021. Across his career, Dr. Horne has made exceptional contributions to geothermal energy, reservoir engineering, and the global geothermal community. His leadership has helped shape both the technical direction and the international advancement of geothermal development, making his perspective invaluable for today's session on geothermal resources, opportunities, and challenges. Dr. Horne, thank you for joining us today. We're honored to have you with us, and I will now turn it over to you.
Very good. Thank you very much. Let me share my screen. Can you see that okay?
Not yet. Yes, now we can see your screen.
Okay, so thank you for the opportunity, and I'm happy to start off this series of very interesting looking discussions you're having on geothermal. So I'm going to try and set the stage today as to where we're at and where we're going in geothermal right now. So to begin, just a quick introduction to geothermal for those of you who just walked in the door. In the process of geothermal energy production, we're doing something very similar to oil and gas. We're producing hot water and sometimes steam from the ground, converting it into electricity, or sometimes using it directly and then returning the cooled water back in the ground again. So production injection is very similar to oil and gas, although there are some important differences that I'm going to emphasize as we go through. That the hot water itself doesn't actually have any particular value. It's not the fluid we're trying to produce, but the energy that carries with it. One of the important distinctions between geothermal and oil and gas is that the value, the energy value of a barrel of hot water is about 1/50th of the barrel of oil. And the consequence of that, even though people have been making money with geothermal for decades, in order to do so, they have to produce massive amounts of fluid and put it back into the ground. So a typical geothermal well in operation today produces 50,000 barrels per day of water. That's kind of a norm. And that's something to bear in mind when we're talking about things like converting oil and gas wells. So there are places in the world which use geothermal a whole lot. Turns out number one in the world is Kenya, who produce almost half of their electricity from geothermal. But you can see here on this list, there are several other countries produce a third or quarter, something like that. So geothermal is important. It's very useful in places where it's available, and it's been steadily growing for decades, back all the way since the 1970s. However, although it's been growing, and it's growing today as well, it's growing in kind of a linear fashion, unlike wind and solar, which have been growing exponentially. And the target that we have, at least the IEA has for a net zero scenario, is a growth to 3 times of what it is today or what it was in 2020. So the big question is, how do we get there, given that we have just been marching steadily but rather slowly forward with conventional geothermal? Before I get to that, I do want to point out, that geothermal isn't new, including in the United States. The United States is the #1 producer of geothermal in the world. And over here on the West Coast, California produces nearly 6% of its electricity from geothermal. And our neighbors in Nevada produce almost 10% of their electricity from geothermal. So it's a very significant resource in places where it's available. The problem is, of course, that geothermal energy as it's produced today, I'll call it conventional, requires kind of the Goldilocks combination of geology. We've got to have high temperature, we've got to have water, both of which, in fact, are present in many places if you drill deep enough. However, the third thing you also require is permeability. And again, that's one of the reasons I mentioned those 50,000 barrels a day. If you don't have massive permeability in your rocks, you can't get the fluid to flow through, and you need that fluid to flow through the rocks to actually sweep out that thermal energy, which is our target. So we need to do something more than conventional geothermal if we're going to move up that curve. So what gets talked about today in the context of new geothermal is the so-called next generation geothermal systems. So in contrast to conventional systems we've just been talking about that just occur naturally, next generation systems try to create the missing components where the geology isn't just perfect. As I say, heat and water are pretty much pervasive everywhere in the Earth's crust if you drill deep enough. But it comes down basically to a matter of making permeability. And for the most part today, I'm going to talk about enhanced geothermal systems, which are exactly that, using conventional fracturing methods, borrowed to some extent from oil and gas to create permeability where there was previously none. Closed-loop geothermal systems is an idea which gets talked about quite a lot as well, which does not use fracturing, or for that matter, change the permeability at all. It simply basically produces a conduction-dominated radiator, if you like, of wells drilled in the subsurface. The truth of the matter, as we'll come to a bit later on today, is that there is very little chance that closed loop is ever going to be economic, because the rate of heat transfer by conduction alone is simply insufficient. So, it gets talked up a lot, but actually it isn't very promising at all. So let's talk about enhanced geothermal systems, because that's pretty much the best chance we have to go forward right now. And as we've been discussing, the idea in enhanced geothermal systems is to find a place which has high temperatures at drillable depth, economically drillable depth, and create the permeability by fracturing. And the kind of depths and temperatures we're talking about are 3 to 5 kilometers deep, 7 to 15,000 feet, and 250 degrees centigrade. And if we look at the temperature in the subsurface of the United States, the lower 48 at least, this is a study we did at Stanford. This is at 7 kilometers depth, which is a drillable depth. This is a combination of data from close to 500,000 wells that have been drilled across the lower 48. And for reference, on the color bar on the right, the kind of temperature that you need to generate electricity with a binary plant, which is what is used pervasively in Nevada, as for example, is about 140 degrees, which is that straw yellow color. So what you can see from this map is that at least in terms of temperature, pretty much the whole of the lower 48 is accessible at those kind of temperatures. The big question, however, is at what cost? It's one thing to have it, technically feasible, but it's something else to do it at competitive price, and that's something we're going to talk about today too. So, in order to make that happen, people have been trying enhanced geothermal systems for actually about 50 years. First invented in Los Alamos National Lab in the mid-70s. And there's been probably 15 or 16 of them built around the world today, some of them still operating commercially. But these are the kind of problems that have been required to overcome, some of them still to overcome, to make it a kind of a widespread energy production method. The whole basis of enhanced geothermal systems is to have contact of water with rock. So you have to produce a sufficient surface area of fractures within a given volume of rock in order to be able to sweep out the heat. And actually, that's one of the reasons why closed loop systems are not promising, because it's very difficult to achieve that without drilling literally hundreds of kilometers of wells, which would cost an enormous amount. But putting fractures in the ground and flowing fluids through is not all of what's required. You also have to have some kind of topology of that network of fractures so that the fluid doesn't come back too quickly, because if it doesn't contact enough rock, you don't sweep out the heat. And again, that's what you're after. And then finally, we have to have permeabilities and flow rates which are sufficient to produce electricity. And as I mentioned, 50,000 barrels a day is a kind of a common target, which translates to 80 kilograms per second. That's a reference I'd like you to remember, because I'll show you some examples in a few minutes. And finally, one of the issues of enhanced geothermal systems specifically is induced seismicity. It's not perhaps as much a technical barrier as a public relations barrier, but nonetheless, it's a very important issue, because if you can't maintain a social license to operate, you simply can't go ahead with the technology. So that's an issue which has been experienced in several places and is the subject of research and development as we go forward today. So let's first of all talk about this 80 kilograms per second, and I just pick out an example from my collection here of a typical geothermal well. This conventional geothermal well, water, steam, and total flow. And what you can see here in this particular well, this is a commercially operating geothermal well, is producing about 70 kilograms per second. So, people make money with that. But if we look at some of the enhanced geothermal systems that have been developed over the last 50 years or so, we see something of a different picture. And this example comes from a kind of a pilot project developed by the European Union in Soultz in France. And you can see on the bottom figure there, the production rate of this particular well was about 8 kilograms per second. So that's an order of magnitude smaller than really is required. The field works, the plant operates, but it doesn't produce very much. This is another example from an EGS system that was built in Japan. There's many lines on here, but the pink one is the one to pay attention to. That's the production rate. And once again, that's about 8 kilograms per second. Over time, however, people kind of got better at it. So this is a EGS system in Landau in Germany, not far from Soultz actually, which in 2007 became pretty much the first commercially operating geothermal field, EGS geothermal field in the world. And it was flowing 70 kilograms per second of 175-degree water, producing about 3 megawatts. Somewhat controversial to have this called EGS. They don't even, in the project themselves, always call it EGS, because they actually only stimulated one of the two wells. One of them was sort of naturally permeable on its own already. And on this graph here of temperature, you can also see the comparison between Landau and Soultz, which is actually a few kilometers away, tens of kilometers away. Landau was very advantageous because they had similar temperatures at much shallower depths, so it was much more economic to drill there. And in the Rheingraben, which is in the border between France and Germany, there are 5 EGS projects that have been developed. And if we look at the magnitude of them, these are operating projects. The thing to note, however, about them is that they're basically small, 2-3 megawatts electrical. Rittershofen is a somewhat unusual one in that it doesn't produce electricity at all. It just provides hot water and steam to a factory which is about 20 kilometers away. And for reference, comparing electricity to heat, the conversion from thermal energy to electrical energy has an efficiency between 12 and 15%, depending on the method. So roughly speaking, divide by 10. So Rittershofen, were it to have been an electrical project, would have been 2.5 megawatts electrical. So here's Rittershofen, here's Sulz, another picture of Sulz. So these are operating projects, but they're very small. We're never going to go up that curve very rapidly with these kind of little projects. And we've had a bunch of EGS projects in the United States as well, including these 4 that are listed at the top, which are currently active right now. And importantly, what you can see at the top, the first commercial EGS project put into operation in the US in 2023 was at Blue Mountain at a project that Fervo calls Project Red. They were able to produce 63 kilograms per second, which was, a very useful amount that ultimately had the capacity to produce 3.4 megawatts. Doesn't produce exactly that because it's actually providing fluid into an existing plant. But anyway, this is coming to commercial scale. And then some of these others that we'll talk about right now, starting first with Forge, which is not a commercial project at all. It's the development of the United States Department of Energy trying to develop technology and experiment with technology to move EGS forward. And they began several years ago, 2015 actually. They had initially had 5 projects and they sampled them down to 1, which is in Milford, Utah. Looks like this. And the strategy that they followed in Utah Forge was to drill 2 sub-horizontal wells. They drilled a bunch of monitoring wells for research purposes, but the main producer and injector are sub-horizontal wells that produce down at about 200 degrees centigrade at a measured depth of around 8,000 feet. And they fracture between them. Now, Forge really opened the door for EGS in many different ways, but one of the most significant ones was the transfer, if you like, of some of the ideas and technology for drilling from the shale industry over to geothermal. And what you can see from this chart of their experiences, the different wells marked 1, 2, 3, 4 in order of drilling, is that over time they got a lot faster at drilling with different methods we'll talk about in a moment. 5832, the blue one at the top, is kind of normal drilling rate for conventional geothermal wells. And then you can see as they move forward, they got much, much better. Now, let me just change gears slightly and introduce you to some of our people at Stanford who worked in geothermal. You've heard the Stanford Geothermal Program, of which I'm the director, has been around for 55 years or so. And this happens to be a group from 2016. And I show you this picture to draw your attention to the guy in the middle. This one in the center, his name is Jack Norbeck. And together with a fellow Stanford student, Tim Latimer, who's from the business school, Jack Norbeck and Tim Latimer founded the company Fervo in 2017, specifically with the intent of developing EGS. And Fervo is important to talk about because they have changed a lot in terms of how EGS looks for future going forward. And what Fervo decided to do was to basically throw out the playbook that people have been using for EGS in places like Salts and Hijiori and others, and transfer into instead the ideas from shale gas development. They plan to drill horizontal wells and do multi-stage fracturing all the way along their length. They use propped fractures, which people had never done before, and that's something we can talk about if people are interested in. But and they also used full completions and perforations, again, not commonly done in geothermal. And their first project, which I mentioned already, was the one in Nevada called Project Red, where they drilled basically a 1 kilometer horizontal multi-stage fracturing. They drilled, this is the microseismic monitoring during stimulation. They had 16 stages of plug and perf stimulation in the injector and 20 stages in the producer. And if you remember one of the points I raised about having uniform distribution of flow, you want to have the water moving uniformly through the rock so that you can sweep the heat out. This production log, which you see along the top, shows how much was being produced or injected into each of the 16 stages of the injector. And although it's not uniform, the geothermal community took this as a big success because most of the EGS projects which had gone before it, first of all, only had a few stages, and almost all of them had one stage that took most of the flow, and that is very disadvantageous because you get short circuit and breakthrough. And they put that into commercial operations in October 2023, connected it up to the nearby Blue Mountain existing geothermal plant, which was kind of short of steam, so they were very happy to have the extra, and they had been generating megawatts since that date. Then what they did is they moved on to sort of a brand new greenfield in Utah, which happens to be basically right next door to Utah Forge. So in this map view, what you can see is here is Utah Forge on the right. They're the two subhorizontal wells, 16A and 16B. And Fervo stepped in, leased up the land to the west, and drilled all of these 1.5 kilometer laterals, horizontals in this case, not subhorizontal like Forge. And they are marching out systems across the desert there, 8 wells per pad, with 33 megawatts for each set of 8 wells. And if we look at it in cross-section, we can actually see, interestingly, 3 geothermal fields in this cross-section. Over here on the right is an existing conventional geothermal field, which has been producing since the early 1980s. In the middle is Forge with its subhorizontal wells, and here is Fervo on the western side. And this kind of pink-purple body is the granitic basement, and that's where they're producing the heat from. Blundell field over here on the right, if you look at these dashed red lines, these are the isotherms. And what you can see is that the isotherms come very close to the surface at Blundell, and that's because there are natural fractures in the granite and faults at that location that first of all bring the heat closer to the surface, which is good, and also provide permeability. So there's no need for fracturing over at Blundell, and the system is moving convectively. But again, moving to the west, if you look at the isotherms, you can see that in both Forge and Fervo, the isotherms are basically uniform. It's a conduction-only gradient. And that's good for EGS because you want to make your own fractures at the place that is advantageous for you. Fervo drilled this initial Delano well to delineate the field to figure out at what depth had the temperature they wanted, and then they drilled their horizontals at that depth. And in Project Cape, they're now doing 27, even up to 40 stages of stimulation. And in 2024, they did their first cross-flow tests, and you can see the figures here. They were actually able to produce 93 kilograms per second between a well pair, even actually up to 120 on the good moment, which is enough at the temperature they're at now, 195 degrees, to produce close to 10 megawatts per well pair. And they have 4 well pairs per pad. Currently, there are 3 pads there, so you can see each of them has the 8 wells. Importantly, also, too, you can see that the horizontal wells are not just laid out side by side. They're laid out in a kind of a wine rack position, where it's slightly above and below, as well as alongside each other. And I showed you this graph before about the drilling progress at Forge, how much that made a difference to the economics. Let me show you what happened for Fervo. So moving back to the original project in Nevada, this shows the drill performance for the conventional geothermal wells that were drilled there previously. And this is kind of normal kind of observation for geothermal wells. They take 30 to 60 days to drill at the depth they were at right here. You can see, this particular one right here had problems. They had to go back and re-drill twice, and eventually they gave up. So that was kind of conventional drilling practice. When Fervo came in, they first of all drilled their first 3 wells like this. They were doing something similar to the original performance, but of course to much greater measured depth. That includes the horizontal. But as they went forward and got better at more practice at moving over the technology from shale drilling, they got down to much faster drilling rates, and now they're able to drill to much greater depths, including the horizontal, within 21 days, which is absolutely spectacular for geothermal. That's something that people didn't imagine could be done before. So they had expected to do better over time in a learning curve, but in actual fact, their real experience was much better even than what they expected for the learning curve. They achieved that, in a number of different ways, but perhaps one of the most significant was that they switched over from using roller cone bits to PDC bits, which had been used in geothermal before, but not very commonly. So that allowed them to put much greater weight on bit. They had much faster rates of penetration, and they also had much longer bit runs, which means that they didn't have so many trips. So that made an enormous difference to their drilling costs. And that is important in geothermal because most geothermal projects have about half of the cost associated with drilling. So I showed you this map before. It's generated by one of my PhD students, Mohammed Al-Jubran. You see his picture here. We talked about the temperature. This is the actual cost of electricity at whatever is the most advantageous depth by his estimates. And this was a very in-depth study where he considered the weather, the temperatures, the distance to the power market, and many other things like that, including actually distance from population centers, because again, sensitivity towards seismicity. And for reference, the average cost of electricity in the US is about $70 per megawatt hour. It varies quite a lot, but that's the average. So that's kind of the orange color. So what you can see here is that there's quite a lot of places where we could do EGS competitively, but not everywhere. So the Western states look pretty good. Gulf Coast actually looks good as well. But all of those blues and greens means that you could do EGS there, but it would just cost a lot of money. It would not be competitive. This graph, however, was generated with drilling rates as of 2022, before Forge and Fervo made the advances we just talked about. And if we draw the map again, based upon 2024 drilling rates, the ones I just showed you from Forge and Fervo, the scale is now compressed. So now the $70 per megawatt hour is the straw yellow color. And what you can see now is that it isn't completely everywhere, but there's a whole lot more of the nation accessible for EGS development at competitive costs. For some reason, West Texas doesn't look very good, but a lot of the rest of the country looks just fine, including on the East Coast, interestingly. Now, those ideas, of course, have gained attention by other operators and companies as well. So let me draw your attention to this company called Zanskar, which is actually doing conventional geothermal development, but they took note of the experiences at Forge and Fervo and adopted the same kind of drilling practices. And they drilled a well in New Mexico at a place called Lightning Dock, which was an existing geothermal field, which had a 15 megawatt power plant already constructed, which basically didn't have enough fluid to get it to operate. So Zanskar moved in, interesting enough, from the point of view of data sciences, which is what your group is interested in. Zanskar kind of presents itself mostly as a data analytics company. They actually recently discovered an unknown geothermal field using data analytics and machine learning. But they put a lot of the data analytics and the drilling practices from Forge and Fervo, and they drilled one well into Lightning Dock. You can see here the red one, and produced 15 megawatts just from that one single well, which is a very significant amount. Most geothermal wells produce around 5, good ones maybe 10. 15 is spectacular. And once again, if you look at the comparison between PDC drill bits compared to what they've been using before, the drill times are much, much shorter. So coming back to my list of problems, most of them basically have been overcome. So achieving the 80 kilograms per second has been achieved. Fracture placement in order to get uniform or kind of uniform distribution has been achieved. And sufficient surface to volume ratio has been achieved by making multiple stages of fracturing. Induced seismicity was not an issue at Fervo. They've drilled more than 30 wells and fractured them without producing significant earthquakes. It is certainly true that for the next 10, 20 years or so, I expect that most EGS projects are going to be done out in the desert and in places where people don't live, basically just to ensure that it doesn't cause anybody problems. And importantly, we're no longer talking about the 2-3 megawatt projects I discussed from the Rheingraben salts. We're talking now of hundreds of megawatts of electricity. And in southern Utah there, Project Cape, Fervo has built 33 megawatt binary power plants, one for each of their 8 well pad. You can see one well pad in the background of this picture over here, and the power plant is built basically right alongside it, and that allows them to achieve a very small footprint. The pipe networks to connect the well pad to the power plant are very short, and that also saves them a great deal of cost. And this is a picture I took last year of one of those power plants under construction. And I believe that the first power plant is due to start up sometime in September or October. Now, in terms of where we go forward, again, this is a study based on a PhD of Mohammed Al-Jubran at Stanford. If we look at how we can go forward, how much capacity could be achievable with EGS, for reference, this scalability curve, the total electricity production of the United States right now is about 1 terawatt. So clearly, as you go forward with larger and larger amounts, it starts to cost more because you pick the cheaper ones first. But nonetheless, you can see that EGS is competitive with many other energy sources up to a certain point. So this looks at different depths as well as the optimal depth. And if we compare that to the capital expenditure, geothermal does cost more in initial capital cost. However, that translates into still a levelized cost of electricity, which is competitive. And the DOE did a study, sort of so-called liftoff report, is how we can go forward. And they started with a base. This graph shows mostly capital cost, dollars per kilowatt hour, but it also shows levelized cost of electricity on the right. But starting on the left-hand side, the existing base for EGS was expected to be around $20,000-$30,000 per kilowatt. Construction of the whole project, that's the kind of prices they were paying for those projects in the Rheingraben in Europe. But then they started to look at how things could be reduced, and drilling cost, of course, was a very big one. And although being the US government, they didn't name any companies. This 2023 first of a kind, this is basically Project Red, the one I showed you in Nevada, which more or less cut that capital cost in half. And then over here, the liftoff target. That's more or less what Fervo has achieved in Project Cape. And the hope is to go with more and more developers into the future to push that further down. So in comparison to other energy sources, EGS is now looking very attractive. And we have commercial EGS operation already taking place in the US and scalable development taking place starting this year. So let me just jump forward a bit and talk about briefly two other topics that are also part of the discussion. First one is superhot, because there are other companies than the ones we talked about so far. Perhaps the next one, out of the gate is going to be Mazama. And Mazama is also doing EGS, but they're doing it in Oregon in a place called Newberry Crater, which has actually very high temperatures. They're already over 300 degrees centigrade and potentially going up to 400 degrees centigrade. And importantly, they have already drilled new wells. There were a couple of existing ones there in 2025, and they've fractured them at 320 degrees, which is well beyond what Fervo and Forge had done in Utah, which was at 200 degrees, and they've circulated between them in September last year. This is the Mazama site on the Newberry volcano. There's another company called 400C, and 400C has actually a land position right next to Forge and Fervo and Blundell plant. They're actually on the eastern side, and they're planning to develop there. So it's kind of a crowded neighborhood in that part of Utah. And then finally, I want to talk about Quaise, which is in the press a lot because they're talking about using a completely different drilling method based upon kind of microwave lasers, if you like. I'm not sure when that technology will ever be available, but nonetheless, they are also developing an EGS project in Newberry, same place in Oregon, but they are spudding soon their wells, and they're doing so initially with conventional drilling. So they're not dependent on their microwave millimeter wave drilling yet, although they might use it in the future. And then finally, I want to talk about closed loop. I mentioned to you before, it isn't actually a very promising technology, and I'll explain now why. It's an idea that's been around for a very long time. You can see Nikola Tesla talked about it back in 1931 in his later years, and it's been sort of invented every 5 years since then. You can see one example here also on the right, where it was in Japan, so-called Morita design. There's a couple of different designs for closed loop. One is coaxial and the other one is a U-tube. And the problem, as I mentioned to you before, is getting contact, surface area to volume contact. And this was a study done by NREL in 1922, looking at one of the U-tube designs proposed by a company called Avor, which is planning to drill. You can see the design there, right? There's two wells, the blue one and the red one. Each of them in this diagram have 12 laterals drilled out of them, and then the laterals are connected tip to tip to make the kind of the U-tube. So Eva's actually drilled a couple of these, not with 12 laterals, but at least with 2 or 3 successfully. And the technology to do that is really rather remarkable. However, the reason this doesn't produce much energy is because it depends on conduction through the rock into the lateral. So because the conductivity of rock isn't very large, the rock cools down very quickly and then it doesn't produce much energy after that. The only way to get around that problem is to drill hundreds of kilometers of laterals, which is what they propose to do. And that's certainly doable. They were projecting Geretsried in Germany, where they were planning to drill 300 kilometers of laterals in 8 wells, each of them with 12 loops. From this study, the NREL study showed that the only way that they could find that to be competitive is if the drilling cost was down around $200 per meter. And for comparison, conventional geothermal drilling costs is around $2,000 per meter. And even Fervo, which achieved their spectacular results that I just showed you, their drilling cost is currently around $1,300 per meter. So this idea basically only works if drilling costs could be reduced further by another factor of 10, which doesn't seem likely. And I made an online calculator because I got tired of explaining this to people, that shows actually how the energy runs down so quickly because of the conduction loss. And we should also talk briefly about using old oil wells. People have talked about that quite a lot too, and it's not a bad idea. People have done it a couple of times. This is one example from Rocky Mountain Oilfield Testing Center in the infamous Teapot Dome field, where they took the entire flow rate from all of the water being produced by the field, which was about 40,000 barrels per day, put it through a power plant, and they produced a few hundred kilowatts. They did the same thing in Huabei oilfield in China, which had a somewhat higher temperature. And we did a study looking at produced water from the LA Basin oil fields, Los Angeles Basin, which have a lot of old oil fields with very high water cuts, 97%. And the geothermal gradient is decent in that area. So we have some temperatures. Remember, we're looking for 140 degrees or so. There's quite a few fields that actually produce water of that kind of temperature already. So we worked out, how much you could produce, and certainly there are some which could be produced. However, the total sort of feasible production of the entire Los Angeles Basin, which is a total of 35 fields or whatever, we picked the 7 that were the most economically attractive. The total potential production is around 7.5 megawatts. So it's not a large amount. And the reason why, as I drew your attention to right back at the beginning, is that you just have to produce a lot of hot water to make electricity. And I think I'll stop at that point because I want to leave some time for questions. So thank you very much.
Thank you, Dr. Horne, for the insightful presentation. The visuals and the examples were especially helpful in framing both the technical challenges and the broader opportunity in geothermal energy. I also wanted to ask, as we continue building student involvement in this geothermal initiative and the upcoming competition, given the strength and reputation of the Stanford geothermal program and the caliber of the students and the researchers working with you, if you feel like there's anyone who may be a great fit, we would be very grateful if you could connect them to Ms. Pan or Dr. Sharma after the session.
Yes, I certainly will. You should have some of the people from Zanskar who are focused on data analytics, particularly for your group. another of our PhD students, Noe Pollack, is kind of their chief data engineer. I'm not sure what her title is, but anyway, she works for Zenska.
Okay. Dr. Horne, several attendees are asking whether today's slides may be available after the session. Would you be open to sharing them with the organizing team, or would
Yes,
you
I
prefer that
can
we
send them
direct?
to you.
Okay, awesome. So we will now move into the Q&A portion of today's session. For everyone attending, please feel free to place your questions in the Q&A box. I can already see the webinar chat and the Q&A box lighting up, which is always a great sign. So let's jump right into the audience questions. I will be reading off them. We have several questions coming in, so we'll take as many as we can during the session. If we're not able to get to every question today, please feel free to share them on our LinkedIn post after the session, and we'll do our best to address them there as well. Moving on to the first question. The first question asks, Dr. Horne, do you see AI-driven subsurface models, automation, and robotics helping in reducing costs and reliability? What do you envision can make geothermal more successful?
It's kind of a difficult answer to give to this particular group because at the moment, I'm not sure that we are data poor or data analytics poor either. The big advances that have been made, some of them have been data analytics that I mentioned from Zanskar, but for the most part, the big advances have been made in drilling, number one. I mean, we talk about actual implementation and deployment of the power plants themselves. That's not to say that I don't see a place for data analytics because we still have to find good locations. The idea of geothermal anywhere is kind of a hope, but it's not realistic, actually. It could be realistic, but obviously, if you want to make the most advantageous project, you've got to pick the best places that you can. And how do you find those? It's still the same for enhanced geothermal systems as any other resource development. You want to find the right location with the right kind of temperatures, the right kind of rocks, not too many natural fractures, etc. So that, again, is a data exploration problem.
We have another interesting question. Are there any of these projects extracting minerals as an additional revenue stream?
Yeah, so people have talked a lot about producing lithium from geothermal brines, and some of the geothermal brines have relatively high concentrations of lithium, specifically those in the Imperial Valley in Southern California, and in other places too. That is a potential extra revenue stream, and there's several companies now trying to do that. Nobody's yet done it at commercial scale. There's been pilot projects that do work, but the pilot projects at least were not competitive in price with conventional lithium extraction methods. But doing it at larger scale certainly has the potential or possibility of adding that stream. There was at one time a zinc extraction plant in the geothermal fields in the Imperial Valley too, but it ran for a few years and then the worldwide zinc price collapsed and they eventually went out of business.
That's exciting here. So our next question is, when water is circulating through the fractured network to extract heat, is there a possibility that the water becomes contaminated with formation fluids, dissolved minerals, or other subsurface constituents?
Yeah, so yes, the answer is yes. So basically, the first thing to remember, these are not oil fields, these are rocks with water in them. So the rocks are basically in equilibrium with the water, so they have minerals dissolved in them. And scaling and corrosion can be a problem in conventional geothermal systems, but it's a problem which is largely in hand, much in the way it is for oil and gas developments too. We have corrosive waters and scaling there too. So that is an issue, that is an engineering problem that has to be addressed, but it's not kind of a game stopper. People know how to do that in most cases.
Another interesting question, is tectonical activity experienced during the process of EGS in terms of pressure changes in the formations and the observations of any monitored earthquakes at the surface?
If I understood that question correctly, the answer is yes. So every EGS project, as actually is this case for shale as well, has an extensive seismic monitoring network, mostly because they require it in any case to monitor the fracturing process. So, I mean, there's microseismic activity all the time. You can't feel it. Humans can't feel it, but seismometers can. And they use that to actually geolocate the fractures to see which direction they're going, to evaluate the treatment. But of course, in the case of EGS, they're also doing that to monitor for potential earthquakes. So, the seismic arrays are a kind of a standard part of EGS projects, and for that matter, conventional geothermal projects as well.
So our next question is, how long does the infrastructure for geothermal energy last?
That's a good question. So typically, power plants of any kind, even natural gas-fired ones, are kind of imagined to have a life of about 30 years. That's the economics are based on that. And that's the case, excuse me, for geothermal as well. So for reservoir engineers out there, what you really want is a reservoir which keeps running for 30 years and keeps the power plant going for its full life. The truth of the matter is, however, that most systems are developed conservatively because you don't want it to run out after 10 years, because then you've got a power plant which is just no longer in use. And we have many examples of geothermal plants now which have been in production for 50 or 60 years. So the Wairakei geothermal plant in New Zealand was built in 1958, and it's still in production. It's almost as old as I am.
That's exciting. So another question is, I have been wondering whether integrating processes that are relevant to EOR, we do have research on CO2 foam injection for geothermal, would lead to enhanced geothermal recovery. Also, maybe more research into artificial lifts for geothermal other than ESPs could be really beneficial.
Yeah, so geothermal wells basically come in two flavors. Conventional geothermal wells and EGS probably will have variants as well. In Nevada, where the temperatures are lower, 140, 150 degrees, all of the wells are basically, production wells are pumped. And ESPs are not commonly used in geothermal because the temperatures are high. They do sometimes use them, but the more common application is line shaft pumps because they're much more robust and all of the fragile equipment is on the surface. So pumped, efficiency of pumps is something which could be helpful. ESPs that were more robust against higher temperature would be useful as well. And an example, once again, is Zanskar, like the one I told you in Lightning Dock. That well that they drilled that produced 15 megawatts, they took advantage of the technology that Fervo and Forge had used with measurement while drilling, which was new for geothermal because of the temperatures. And they drilled that 15 megawatt well perfectly straight and vertical. They weren't trying to go horizontal, but they did want to make it perfectly vertical because of the line shaft pump. So they have a nice straight well. They don't have to have their line shaft going around corners, and they can get the maximum efficiency from the pump. And that's a good thing.
Another question we have is, given the technical overlap between petroleum engineering and geothermal development, what do you consider the most critical capability that petroleum engineers must adapt or rethink when moving from hydrocarbon reservoirs to geothermal projects, especially if the goal is to scale an idea into a viable business?
So I think that the two things that I have seen, I'm also a petroleum engineer myself, so I think that the two issues that petroleum engineers sometimes not struggle with the concept, but just adjusting their mindset between oil and gas and geothermal. Number one is the flow rate. I talked about that before. So the magnitude of the flow rate is so much greater in geothermal that it requires different well construction. Geothermal wells are basically never using tubing. They're drilled to 13-inch diameter in some cases because you would need that diameter to have the massive flow rates. And then secondly, the other issue too is that the fluid production is not the target. So the fluid itself has no value. You have to think of everything in terms of thermal energy. And, that is not, the first problem in oil and gas engineering, where we think of everything as isothermal. People don't worry too much about the conductivity of the rocks. And from my kind of separate opinion, it's one of the reasons why closed loop has gotten, invalidly so much traction, is that people think about producing the fluid, not recognizing that it doesn't really produce the energy, or at least it doesn't for very long.
Okay. In the interest of time, I think we can end the Q&A session. To everyone whose questions we couldn't get to, please feel free to ask them on our LinkedIn post, and we will do our best to address them there as well. And on that note, Dr. Horne, are there any final remarks you'd like to share with our SPE young professionals and students group?
I think the geothermal industry is just right now going through a big renaissance, and we're going to see tremendous advances, hopefully getting to that exponential growth I talked about in my first couple of slides.
Absolutely. It's very exciting times for all of us. So thank you, Dr. Horne, for sharing your time and insights with us today. On behalf of SPE Data Science and Engineering Analytics and the Geothermal Learn-to-Launch organizing team, I would also like to thank Ms. Sushma Bhan and Dr. Pushpesh Sharma for giving students this wonderful opportunity to be involved in organizing this initiative and gaining exposure to geothermal energy and learn from leaders in the field. To everyone who has attended, we hope today's discussion provided a strong foundation for understanding geothermal resource types, technology stacks, market opportunities, and key challenges shaping the future of geothermal energy. Thank you again, and we hope everyone has a great rest of the day.
Thank you.
Thank you, Dr. Horne. Thank you, Divya. Thanks, everyone.
Thank you.
Very good. So I will send these slides to you, Divya, shall I?
Yes, please.
Okay, I'll